Hi everybody, this is part 1 of section 9.1. We're going to talk about sequences. I apologize, I have a little bit of a cold and a cough, so I'm a little stopped up, but hopefully it won't be too bad. So this is what we covered in today's lecture. Normally I'll be recording the live lectures, but we had a little bit of technical difficulties in class today, so I'm just going to record this in my office so you can get caught up on all the material you missed today. We're just going to start Unit 3 kind of fresh. We're just going to wipe the slate clean. So I spend a little bit more time on Section 9.1 than other classes because I think it creates a lot of opportunities to review some Calc 1 concepts, some algebra concepts that you're going to need for the rest of this unit. And one thing I can definitely tell you is limits are about to become your best friend. Unfortunately, when you see limits for the first time, you're kind of doing the worst thing we do with them, which is talk about the definition of the derivative. But today and moving forward, you're going to see that limits really are the secret to your success in Unit 3. So let's get started, and we'll first start off by defining what a sequence is. So a sequence, right, is a collection of terms and I think it's useful if you think of them really as a list, okay? And so it's not just a finite list of terms, because that would be a set. This is actually going to be an infinite collection of terms. Okay? These terms are ordered. And have a discernible pattern. Okay. So the ordered part kind of gets forgotten about when you get toward the end of this, but these sequences, the reason the order matters is we've mentioned that there's a discernible pattern at play. So if you don't list the terms in the specific order they're meant to be listed, then you're actually violating the pattern and actually in some cases changing the definition of the sequence. So you'll see when we start generating these things that the items that appear in your list are happening in a very specific order for a reason. The other thing I want to define kind of right out front is when we talk about sequences, we're going to talk about whether they're convergent or divergent. So let's kind of explain what we mean really quick and define convergence and divergence. So convergence right? We say if the infinite limit, right? Remember, we're talking about sequences here. So of a sequence exists. Then the sequence converges to that value, right? So if we want to check a sequence for convergence, we'll look at the limit as n goes to infinity. If we get an answer, then we'll conclude that the sequence converges to that value. So another way of looking at it would be saying, well, if the limit as n goes to infinity of a sub n equals some real value L, then the sequence a sub n converges to L, right? And so we're going to actually do some examples, explain what we mean. These little curly brackets you see right here, typically we use those around a set of numbers. Just remember your set will be infinite. So when you simply see the brackets around of an expression, what we're telling you is that expression generates that set, or in our case, generates a sequence for us, right? Divergence is typically explained by just simply saying if something doesn't converge, then it diverges, right? But we can be a little more specific than that. So we can say, well, if the infinite limit of a sequence does not exist, then the sequence diverges. Okay? So just like we did above, we can write that kind of in a mathematical sense. So I can say, well, if the limit as n approaches infinity of a sub n does not exist, or if the result is positive or negative infinity, then the sequence a sub n diverges, okay? So let's be clear on this. Some limits, when we evaluate them, and we're going to see examples of this, you can't evaluate the limit at all. You can kind of look at it and see, oh, this thing is never going to exist. Or what could happen is you could get positive or negative infinity out of the limit. And positive and negative infinity is a version of does not exist. It's just a more specific classification of does not exist. So here we're simply saying I can't find the limit at all. Here we're saying, well, the limit doesn't exist, but I can tell you why the limit doesn't exist. So the terms are all blowing up to positive infinity, or they're all blowing up really big in the negative side of things, and so they're blowing up to negative infinity. So clearly both of these cases aren't providing us a real result that we were getting back here, so we would conclude that the sequence diverges. So when we're looking at a sequence, if we kind of go back to the original definition we've got here, we're either going to give you the pattern in the form of an expression, and then from that pattern you could generate the list of terms, or we might show you the list of terms and then you identify the pattern and then you can write back what the expression is. So let's do an example first where we just look at how do you generate the terms of a sequence if you're given the expression that generates them. Okay, so to generate the terms of a sequence, excuse me, the letter here, A, is the term itself, okay? This little subscript that we put underneath here, this represents the nth term, right? Or you could think of it as the order. So if you're evaluating a function, right, we have f of x, it's a well-defined equation, and I want to know what f of 3 is. Well, we would just plug 3 in everywhere we had a variable. Well, it's a similar situation with sequences. If I want to know what the third term of the sequence is, well, then I plug in 3 for n everywhere I see an n in the expression. But keep in mind with sequences, n is usually going to be our variable. It's how we index things. N is a counting number. So if there's no information given about where you're supposed to start counting from, it's always assumed we start from 1. If we decide to count from another number, like we say this one starts at 0 or this one starts at 2, it will be well defined in the expression. So typically for these sequences we're going to look at right here, we're just going to start counting from 1 and move up from there. So if I want to generate the first term of this sequence, right, a sub 1, well, that means I need to plug in a 1 everywhere in my expression that I had an n. So 3 plus negative 1 to the n, well, negative 1 raised to the 1 is just going to be negative 1. So we're really just getting 3 minus 1, which is 2. If I want to find the second term of my sequence, well, if you square negative 1, you're going to get positive 1. So this is really just saying 3 plus 1, and we get 4. When I get the third term, well, negative 1 cubed is negative 1 again, and I can see that I'm getting a 2. Well, I've already generated enough terms of this sequence. I can see the pattern that's emerging, right? All the odd terms, negative 1 is going to stay negative, and we're going to get 2. All the even terms, negative 1 is going to become positive, and we're going to get 4. So I can actually keep generating subsequent terms of this sequence without actually plugging them into the expression, because I can just see, oops, messed up there. I can just see that it's just going to alternate between 2 and 4. And this would go on all the way up to positive infinity. All right, let's look at another one. So this sequence, right, is n over 1 minus 2 to the n. So if I want to generate the first term, I plug in 1, and I get negative 1 over 1, right? The numerator's 1, the denominator's negative 1, but I just personally like to move those negative signs into the numerator. So it's actually a good idea when you're generating a sequence that is a ratio like this, that you do, even if it's something silly like 1, like you could call that -1. But when I'm trying to find the pattern, I like to leave it in terms of a ratio because I want to look at what's happening in the numerator separately from what's happening from the denominator. So if we look at B2, well, 1 minus 2 times 2, that's 4. So I get 2 on top, -3 on the bottom, and I'm just going to move that guy into the numerator. The third term is 3 over 1 minus 6, so I'm going to get -3 over 5. Well, I'm actually already seeing a pattern emerge here. So if we list out the terms we've generated, right, I have 1 over 1, or -1 over 1, -2 over 3, -3 over 5, and I can kind of see what's happening here. The numerators are staying negative. They're counting up 1, 2, 3, so I'm pretty sure the next one's just going to follow this pattern, right, and count up 4. The denominators are starting at 1 and then going to 3 and then going to 5, so it's just every other or every odd number in sequential order. So that means this is going to be 7. I could say, well, that means the next term's going to be -5 over 9. So the equation is good to help you get started, but once you kind of see the pattern that's emerging, you can just kind of keep filling in as many terms as you need. All right, let's look at another sequence. So this is n squared over 2n minus 2 to the n minus 1. So we can see here, excuse me, that these sequences can take on many different forms, right? There's no one right way. We have a lot of leeway with these expressions that we're writing. So if I want to generate the first term of this sequence, I'm going to get 1 squared over 2 to the 1 minus 1. So that's just going to give me 1 over 1. The second term is going to give me 2 squared over 2 squared minus 1. So the numerator is 4, and the denominator is going to be 4 minus 1, which is 3. The third term, right, is 3 squared over 2 cubed minus 1. So that's going to give me 9 over 8 minus 1, which is 7. So if we start listing out the terms of this sequence, I've got 1 over 1, 4 over 3, 9 over 7. And, you know, this pattern's a little more challenging, but we can see, well, the numerators are just going up in squares. That's what the numerator says. So I actually know the next one's going to be 16, right? We have 1 squared, 2 squared, 3 squared, 4 squared. The denominator's a little trickier because you've got to go up to the next power of 2 and then subtract 1. Well, if 2 cubed is 8, then you double it again to get 2 to the 4th, which is 16, and when you subtract 1, you get 15. And this would continue on all the way to infinity. Now there's another way we could define a sequence, right? The first 3 we just looked at, they were all defined by expressions. Well, another way you could define a sequence is called recursively. So with these sequences with a well-defined expression, if I wanted to look at sequence A, B, or C, and I said, well, give me the 10th term of that sequence, you could easily generate that by just plugging in 10 for n. Recursive sequences are a little bit different. Okay, the next term is dependent on previous terms. Okay, so there are multiple ways you could define a recursive sequence. So we could make it only dependent on one of the previous terms. We could make it dependent on multiple previous terms. So the most famous kind of recursive sequence that most people have heard of is the Fibonacci sequence. And the Fibonacci sequence, you start with 1, 1, and then it's generated by adding up the 2 previous terms. So, oops, sorry, Fibonacci, my bad. The Fibonacci sequence, right, the first term is 1, the second term is 1, And then the third term is by adding the previous two terms. Now, some people call the first term A0 and the second term A1, and then they start counting from 2. It's okay as long as you're clear about how you're indexing. We can actually define these in multiple ways. But if you want to see what the Fibonacci sequence looks like, right, you start with 1, 1. The third term comes from adding the previous two terms. So 1 and 1 is 2. Then the next term comes from adding its previous two terms, which that's going to give you 3. And then you're going to get 5, and then 8, right, and then 13. So the Fibonacci sequence was kind of a major plot point in the movie The Da Vinci Code, but it's a pretty well-known sequence even by non-math people. So let's look at a function or a sequence that's defined recursively. So we'll call ours D, and D1 is 25, but Dn plus 1 is found by taking the previous term and subtracting 5. So if I'm starting at n equals 1, well, when you plug in a 1 here, what we're really saying is D2 comes from taking the D1, which was the term previous, and subtracting 5. So this sequence is kind of easy to list out. We start with 25, and then we remove 5, and then we remove 5 again, and we keep going, right? And eventually we're going to end up at 0. So what do you do when you end up at 0? Well, you keep going. We already saw in our previous sequence B that these terms can be negative. The n values that you plug in cannot, but the actual result of the sequence can be. So then it would go to -5, and then -10. And so just by looking at this sequence, we can see that this sequence is actually going to diverge because it's going to go toward negative infinity. So the way that we decide, once we kind of know how to generate a sequence and we understand what a sequence is, the next big question we want to ask is, well, if you're shown a sequence, does that sequence converge or diverge, right? And it's not always feasible to look at the terms. And sometimes even if you list the terms out, you can't always see what value that the list is approaching. So we do that by using the limit. So if we want to find the limit of a sequence, the first thing we need to do is we need to revisit just some old ideas about limits. So your new best friend in this class is going to be L'Hopital. So let's do a quick review of L'Hopital's rule and actually talk about what's going on here. All right? So L'Hopital's rule actually states that if you're taking the limit as x approaches a. So one of the things I want to make sure you understand at the beginning, the actual definition of L'Hopital's rule says x can actually approach any value. So it could be 3, it could be 1, it could be infinity. So it's very general. We're writing the general formula here. It can approach any value, and we're taking the limit of some rational expression. Now, we write it as f of x over g of x because we want you to understand that we're not asking you to look at this ratio as a whole. We want to look at the numerator independently of the denominator. So we write them as their own expression here. So if the value of this limit comes out to be 0 over 0 or some form of infinity over infinity, then L'Hopital states that the original limit that you were looking for is actually equal to the limit of the numerator, the derivative of the numerator over the derivative of the denominator. So this is why this is important to not treat this as one fraction, because some students will remember that I'm supposed to take the derivative, but then they might apply the quotient rule. And if you apply the quotient rule, it's not really giving you what you want. The quotient rule is just giving you the derivative of the entire expression. But what L'Hopital's rule is actually saying is, well, if the numerator is going to 0 and the denominator is also going to 0, well, the question is which one's getting there first, right? And the same thing could be asked about infinity over infinity. If they're both blowing up to infinity, which one's getting there first? So if you think way back in the beginning of Calc 1, the derivative was really the rate of change. So what this is actually telling you is how fast is the numerator going to 0 or infinity, and how fast is the denominator going to 0 or infinity. So the general rule of L'Hopital is, if we end up in this situation, we take the derivative, we simplify the expression, and then we try the limit again. If we're still in this situation, well, then we take the rate of change again. So you look at the second derivative over the second derivative. And we keep going until we get an answer. So I'm just using the constants n and d. N's going to be for numerator, d is going to be the result of the denominator. If you get an actual constant in the numerator and the denominator, that's great, you're done, and that's the limit of the original expression, because all of these are going to be equivalent in terms of limits. However, what happens if you don't end up with a numerator over a denominator? So really, what we're going to play here is a game of numerators and denominators. All right? So what do we do if something funky happens, with our ratio, and how do we interpret our results? So one thing that could happen, because remember, these zeros and infinities could crop back up. So what if you run out of 0 over 0 situations, and the limit gives you a 0 in the numerator, but a constant in the denominator? Now, what I'm saying here is, I'm assuming that all we're comparing is the far left side of the equation with the far right side of the equation. You may or may not have had to take some derivatives to get to this point, right? But let's say we took the first derivative over the first derivative and we ended up here. Well, what this is telling you is that the original limits were probably going to 0 over 0, but the numerator gets to 0 faster than the denominator gets there. So we would conclude that the limit of this expression is just 0. Conversely, if the denominator is getting there first, then you'll see a constant in the numerator and a 0 in the denominator. So how do we interpret that? Well, if the denominator of a fraction gets smaller, then the whole expression gets bigger, right? Because we're taking something and we're dividing it by something small, so we're going to get more pieces. But if that denominator is collapsing all the way down to 0, then the whole fraction is actually blowing up to infinity. So the result of your limit would be plus or minus infinity. It will be positive infinity if n is positive. It will be negative infinity if n is negative, because you're taking some number that's positive and dividing it into infinitely many pieces, so there will be positive pieces, or you're taking a negative number and dividing it into infinitely many pieces, and those pieces will remain negative. Right? But what if the original expression returns infinity on top and a constant in the denominator? Well, just like in the case above it, if the numerator's getting to 0 quicker, the whole thing was 0. Well, if the numerator is still blowing up to infinity, then we say the limit is positive or negative infinity. So the numerator kind of dictates the answer in this case. If we end up with infinity on the bottom,